Our next speaker will be Rob Probin, and you will be talking about RISC-V assembly. Rob, we're looking forward.
Hi, can you all see my screen?
Yep, we see it and we hear you.
Let me go, in fact, let me go into presentation mode and then just full screen. Okay, so I think I'm going to split this presentation. Maybe I'll do one next time because there's maybe a lot to talk about. I thought I'd start with seeing there's been a lot of chat about RISC-V on the mailing list, and also Peter gave his excellent presentation. I thought I'd start with maybe giving an overview about RISC-V. So it's become quite popular. Now, I think there's a few reasons for this. One is to do with ARM licensing costs. So a lot of the manufacturers obviously have to pay licensing to ARM. There was a very expensive architectural license available at one point. So Apple, for instance, had an architectural license, and that allows them to do what they want. But for most microprocessor, microcontroller manufacturers, that they can't do what they want. They can only adapt peripherals and compete with peripherals. So if you ever think about Atmel, now Microchip and ST, they've effectively got to produce exactly the same cores, which is good for software engineering, of course, but it doesn't allow any differentiation maybe on the core itself. So originally, I'm sure that a lot of the manufacturers use this as a bit of a stick, RISC-V as a bit of a stick to beat ARM with, but I think it's actually gained a whole bunch of traction on its own. It's a lot of people with attention and obviously there's a lot of hobbies. There's a lot of very exciting new boards with multi-core, multi-processing. So I think it's for anybody who's outside it, it's quite complicated, right? Or it appears quite complicated, although it's actually very elegantly done. And I guess it's relied on the sort of experience of the last 40 or 50 years of making microcontrollers, microprocessors. So the basic sort of cores you've got either 32-bit, 64-bit, or 128-bit, and they've got a suffix after them generally. So here are a few. So 32i is a basic integer instruction set. There's a version called 32E, which is exactly the same as the 32i, except it only has to support 16 registers. And then there's a 64i and a 64E and a 128i. I won't talk about the weak memory ordering. And then there are extra bits, right? Common extensions. There's a long list of official ratified extensions, and there is a bunch of non-ratified. So, for instance, the compressed instructions. This is a bit like ARM Thumb or ARM Thumb 2. That's got these 16-bit instructions. So there's a small subset, and the way the opcodes are laid out, they've effectively left themselves space to do to the 16-bit opcodes and to do a whole bunch of extra exciting things. The M is a standard for integer multiplication division, and maybe very small cores, and I'll show you one in a minute. If you're using a very small microcontroller, you might not need multiplication division, although it's very common, obviously, on everything above that. F is standard single precision. B is bit manipulation. So these are all different subsets of the instruction set. But there's also defined ways for a manufacturer to extend the instruction set, and I'll show you a bit about that in a minute, which allows a large population of people to do innovation in RISC-V. So, and in fact, before I even go here, let me just switch and talk about Peter's core. So Peter, I think on these Milky cores, we're using this 906 core. So this is the 906. It's got GCV, and it also notes, for instance, it's got the F and the D instruction sets and the V instruction set, which is where this V comes from. So just let me go to the spec. So this is the RISC-V ISA. So you can see So G is a special general. So G includes I, integer. So it's got the integer set. It's got M, multiplication division. It's got A, it's got atomics. And as you might imagine with these quite powerful cores that Peter was using, he'd want atomic primitives. It's got D, which is double precision floating point. It's got this long thing, which I'm not going to even try to Z fancy, which is the fencing instructions. This is memory fencing for instruction fetching. It's also got F, which is the single precision floating point, and it implies this control states and register access. So you can, from the after they mention the part name, they will talk about which core it is, and you can see very clearly which bits it's got. Yeah, which makes the whole decoding what particular instructions you can run on it. As I said before, nearly all of them got the instruction, the standard integer instruction set. Let me go back to my presentation. So let me talk a bit more. These are sort of the maximal picture of the registers, and they've got this x x0 to x31. Now, with the embedded a version of the integer instruction set, so all the embedded processors. Embedded registers, sorry, embedded integer registers. Sorry, so X0 to X31 are the integer registers, and the embedded version for when it builds small core is just X0 to X15, right? And they've got a bunch. They've got an alternative name, right, for helping you memorize the things. And the first few generally, and this is to do with the application binary interface, and it's less important for Forth. Obviously, you can implement it as you want, right? But if you wanted it to have linking compatibility with like C libraries, you'd want to comply with these. So X1 is typically the return address. That's like link register in like PowerPC or ARM. They've got a one that's typically used for the stack pointer, and there are some stack pointers, especially in the compressed instructions. There's some stack pointer. You have to decide which stack pointer you want to use it. There's global pointer. Maybe if you had an area of memory that was global, because these are RISC instructions. Obviously, addressing is limited, right? Unlike a CISC where you can have a full 32-bit or 64-bit, 128-bit address. Generally, for a single instruction, the addressing, the size of the immediate value for the address is limited. So you might want a global pointer, a thread pointer potentially, and then you might have these X8, for instance, is either a save register or a frame pointer. So frame pointer is obviously a way of referencing local variables potentially if you're on that sort of type of machine as opposed to Forth, and then. This, again, the saver at the end is part of the application binary interface about whether the core or the curly saves it. It's less applicable for Forth systems. And then the other thing to note is that and the compressed instructions, I'll show you a snippet of that later on. You can address any of the integer registers on the standard instructions, but on the compressed instruction, you can only address X8 to X15. So when you set in your core VM for your Forth, you obviously want to figure out there's going to be a bunch of things that you might be doing, returning the return stack or the data stack that you want to have very, very efficient. Especially if you've got a very small core, Peter Forth's core was a giant 64-bit core with lots of memory. But if you're on a very small embedded target, then those compressed instructions really make a difference. Even on the bigger cores, they can make a difference because obviously you use less cache. So let me give you this one is the one that's been on the list a few times. I think Peter Jackie's talked about this a bit. This is the smallest RISC core that I know of. It's less than 10 cents at retail volume. So if you go into AliExpress, you can buy 10 or 50 of these, and they're much less than 10 cents. Sometimes you get less than 5 cents. They come in a variety of packages, 8-pin, 16-pin, 20-pin packages. I've put all the stats there, but they're just tiny. They've got 16K flash, 2K RAM. There are bigger versions. WCH do bigger versions of this chip with more memory. But I wanted to highlight a bit highlighted is what type of core it is. So uh, uh, a RISC-V 32-bit embedded, which means it's only got 16 registers. I might note that register 0 is always hard coded as 0 in hardware. So if you want to get 0, you can read register 0, and that'll be a 0 always. So you've only really got 15 registers on the embedded instruction set. It's got the compressed instructions, and it's also got this custom XW extension. So this is one of the things where they've tried to innovate, and they've added a bunch of half-word and byte operations. So as you might imagine, this processor might be used as an I/O processor, perhaps reading, and you could use it as a very cheap analog to digital converter. So if you buy an off-the-shelf analog to digital converter, even a low bit one might cost you 50 cents off DigiKey. This thing's got 6 to 8 channels of a 10-bit ADC. So you might be able to use it as a I/O peripheral. And this is actually part of what myself and Peter Jackety have been talking about, using this type of small core as a universal peripheral, but have it talk forth so it's programmable, right? So it's a programmable I/O processor. I've put some of the it's also got a bunch at the bottom. It's got a bunch of extra features that they've added in, like you don't need a vector table necessarily. It's got acceleration for epilogue and prologue code. I haven't looked at whether that'll be good useful in my fourth implementation. Said we're doing a native fourth implementation. Let me just flick forward now. This screen card. Let me show you this. Right, this is quite a good aid memoir. So that they do this. I'll post this as a PDF on the fourth 2020 group, and I think we're collecting the presentations in a separate area as well. But this has got like a summary of instructions, and originally it looks like a wall of text, but it's actually very easy. You've got your stores and your loads, you've got your shifts, you've got arithmetic, you've got logical instructions, compare, branches, branch and link, and then I won't go through all of these, but you've got these are the compressed instructions. So these are the things you quite often need to do quite often, load and store, and some basic arithmetic. These load immediates and load opera immediates. So this allows you to use 2 instructions to load effectively an address potentially very quickly. And it's got a few basic branches and jumps, and things like the subroutine jumps, the jump and link instructions are 16-bit instructions, right? So let me just switch off that. And then it's also got a whole bunch of stuff. There's more to this. It's got all the different stuff as well. And it also tells you what the encoding, the instruction formats are. Let me go back to my presentation. So there's also a few pseudo instructions for if you're programming an assembler, like for instance, ret is actually a jump to the link register, jump to the link register. So there's a few of these pseudo instructions you might want to use just as an easy way of thinking about things. Here's a tiny snippet of code. So for instance, you might at the beginning, this is actually a piece of code at the beginning of the VM where we're loading I think actually this is out of demo code. My what's it called? This is the out of the VM. So I'm using at the moment X8 to be the return the return stack, and SP to be the data stack, and also use GP to be the RAM, the SRAM start, because as ARM they're like the top nibble is what's on a memory page. So it's 2 top nibble of the 32-bit addresses for RAM, 0 for flash, and 5. So this is just a really simple dumb delay loop, right? Where you load a big value into X6, you decrement X6, and you check if it's not equal to 0. This 0 ends up being X0, the register 0, and then a return. So just a simple example of some code, so you can see that. So there's a whole bunch of load information I'll paste on these. I'll also paste, I won't read through these, right? So I was planning on writing an assembler in Forth, but I sort of got sidetracked and ended up using this project here, this GitHub project, so WNC have got a set of tools, but they're very, I think Peter Jackie's installed them. They've got kitchen sink in them, very complicated. And what somebody's done has simplified the whole process, right? Now, normally this is, I guess you might do, you'd be using C++. I mean, all I wanted was the assembler, the GNU assembler. So there's actually a link to the instructions about how to install the assembler very quickly with a couple of command line commands and that gets you into bin utils, which is RISC-V assembler. To assemble, there's this long command line which I'm just using. I'm going through GCC, which is the GNU compiler collection. Although all I'm compiling is this .s file, forth.s, strangely enough. I'm compiling for the architecture's RISC-32. Now, notice this compiler is listed as RISC-V 64, right? It does RISC-V 32 as well, right? You just have to tell it what architecture it is. I mean, embedded compressed instructions. That's I want it to be instructions and long and pointers to be 32-bit. That's what I'm compiling. That's what I'm outputting. I generally put this in a shell script, or you might put it in a batch file if you're on Windows, because I can't remember this number of arguments anymore. I want to output a list file. In fact, that snippet of code before, in fact, if I just go to this is output the list file, you notice this load immediate has actually generated two instructions, two 32-bit instructions, because it can't generate. It's actually 2001301 is where my D stack init is, my data stack init. So, and then I want to move it from because I want to download it to the target. I'm using the Linky thing that you can get for a couple of dollars off AliExpress. So I want to do an obj copy from. I'm going to get to binary from your elf into the bin. And then there's some notes about what pins you need. So you need they've got a single wire IO pin, which you can debug over. You can download code over. You can also, it's got a simple sort of UART. I haven't got any sample code for that, but it didn't look too difficult. And you use this mini ch link utility, which comes with the downloads from that previous link, and just tell it where you want to load it to. Let me just flick through this. So I'll upload these notes. So this is this is a bit of a notes about if you wanted a debug with GDB, which obviously I'm hoping to get away. Once I've got my first few instructions, got the UART up and running, I'm hoping I can be totally in Forth land and away from. I've used GDB quite a bit, the command line GDB. One thing that's sort of interesting, they've got this, and maybe I can replicate this in Forth actually. They've got for GDB, they've got this SVD file, this is actually an ARM technology for viewing peripheral registers in a simple format. So you can see, the UART registers and you can see which bits are set. It's quite interesting, but I'm hoping to avoid doing that by dropping into Forth land. So this is sort of only the first half of this presentation, really. I figured that would be enough for 15 minutes. I think I've overrun already. I'll certainly get this presentation, but this was to give you a flavor, and you can eventually get into RISC assembler, writing RISC assembler if you want to bootstrap your Forth from scratch quite quickly. And hopefully these notes will allow you to sort of get started within a few minutes. Any questions? Stunned silence.
Everyone's overwhelmed. Thank you very much.
Yeah, very nice.
Great, Rob. Yeah, very good overview of what's going on. Great. And yeah, maybe to add on this, there are also RISC-V soft cores in FPGA, and Matthias Koch, the author of MakeCrisp, he has a very tiny one that he developed along with Leo Oh, I forgot about the name. Sorry
Yeah.
about that. Bruno Levy, he is a French physicist. It's really tiny, and it runs MIG-CRISP force, of course.
Yeah.
Yeah.
Yeah, there's Quintus fourth as well that
Yeah.
obviously runs on RISC-V, so that's what Peter's been using, I think. So it's interesting. Obviously, it helps you if you know a bit of RISC-V assembler, because then if you use words like C to be able to disassemble a word, you can for a native compiler like ME-CRISP, you can sort of get an idea what's going on.
The Quintus I am using on the MIG-5
Yeah.
is a 64-bit version.
Yeah.
And Brad Nelson had also implemented for the C3 of SP32 an assembly in force.
Yeah. It's a nice instruction set.
Really, really nice.
It's quite well put together, the instruction set. I mean, there's things like x86 that no human should program in assembler, although a lot of us have actually done it for against their better judgment, as opposed to something like 68,000 or 6809, one of those sort of nicer instruction sets. x86 is terrible. RISC-V is quite nice. ARM's okay, but RISC-V is quite nice. People have really thought about how it's structured, so.
Well, I lost it for the x86 just with all those SIMD instructions, SIMD instructions. There are too many of them, and they're used for everything.
Yeah, it's terrible. It's got out of hand entirely.